next presentation, which will be given by Meng Zhang. She's a collaborator in our interventional MR unit here in Lausanne. She's here for a year now, and she will present you some new ideas, or not new ideas, but
somebody has to switch off
procedures.
There is a noise, Professor Svita. Somebody has to switch off.
I will go out. So I will. Good.
Okay. Good afternoon, everyone. It's a great honor to speak here today. I'd like to thank the organizing community for the invitation and Prof. Illustrator for his support. Today, I will talk about catheter tip imaging in interventional MRI. We'll start with clinical backgrounds, then look at artifacts and how tip coils can help. Next, I'll compare slice imaging with tip imaging, followed by a look at the visualization mechanism behind tip signal. And finally, I'll show some preliminary results from our experiments. Let's now talk about the technical challenges we face in conventional cardiac MRI. First, most standard MR receiver coils are relatively far away from the object to the image, which is in our case the heart. The distance results in poor signal to noise ratio. Second, slow conducting channels is very thin, which means it's often represented by just a few voxels on standard MR imaging. This makes accurate tissue characterization extremely difficult. Another key issue is that the signal is easily affected by partial volume effects and interference from adjacent structures such as the blood pool or lungs. If we want to increase the spatial resolution, we can reduce the field of view. However, with conventional surface coil, this leads to wraparound artifacts, which can obscure anatomy details. Let's review the problem of the loss of SNR with surface coils. The top row shows the relative coil sensitivity versus distance, while the bottom row shows the signal-to-noise ratio versus imaging depth. On the left side, we see the signal sensitivity of various surface coils. In different colors, you will see 3-inch in blue, 6-inch loop coil red line, head coil green line, and body coil pink line. And we can see that as the depth increase, the signal-to-noise ratio drops significantly from the surface coil. For surface coil, this means that their sensitivity is the best at the surface, but quickly decay with distance. In comparison, on the left, we introduce some catheter tip coils, which are positioned directly at the target. These coils provide very high local SNR exactly where we need it, even deep inside the body. As shown in the lower plots, the catheter coil can offer the highest SNR at depths, while surface coil lose efficiency. This is important when we try to image small, deep structures like slow conducting channels inside the scar tissue of the heart. We know that myocardium scars can be electrically irritated, but they can also induce arrhythmias if they have slow conducting channels inside. These channels are extremely narrow, yet they may form part of re-entry and trigger life-threatening arrhythmias. However, with conventional surface coil imaging, the typical voxel size is around 10 cubic millimeters. As you can see on the left image, the internal architecture of the scar appears blurry and indistinct. In contrast, catheter tip imaging has the potential to achieve a much smaller voxel size, maybe as smaller as 0.5 cubic millimeters. With that, we would be able to visualize internal scars details with much more clearly, which is crucial for identifying these clinical important channels. In general, the clinical and interventional MRI we encounter several types of artifacts. Here's the quick look overview. Wraparound occurs when the scanned object exceeds the field of view. Susceptibility artifacts result from mantle or air interfaces. Motion artifacts are common in cardiac imaging due to patient breathing or catheter movements. Grips raying appears when there's case-based traction, and RF interfaces, which is particularly relevant in interventional CMR, can arise from cables or nearby hardware. Wraparound artifacts happen when the imaging field of view is smaller than the actual anatomy. In phase encoding direction, signals from the outside of field of view are misregistered. They wrap around to the opposite side of the image. This is especially problematic in cardiac imaging, where the high spatial resolution is needed. But we often try to keep field of view small to boost the spatial resolution. Here are two examples. We observe two classic example wraparound artifacts. In the first image, limited field of view in the anterior-posterior phase encoding direction. It results in signal from inferior anatomy structures, such as the liver or stomach, being structure appears only at the top of the image and obscure anatomy there. In the second image, we see the wraparound artifacts on the left and the right edge. This occurs when the field of view in the left-right phase encoding direction is insufficient to cover the whole anatomy, causing signal from outside the imaging region to fold into the image. Now let's consider a question. Can catheter tip imaging also suffer from wraparound artifact? To answer this question, let's take a closer look at the structure of the catheter. This catheter closely resembles the one currently used in our experiment, an ablation catheter manufactured by Imicor. This catheter has tiny MR receive coils right at the tip, with a very small signal zone. That means even with a small field of view, no signals come from outside, so no wraparound can happen. In contrast, surface coil have a wide sensitivity range and much more prone, so by design, tip coils avoid wraparound artifact. Here we clearly see the difference. On the left, using a surface coil, signal outside the field of view fold back in, causing wraparound. On the right, the tip coil imaging avoids this entirely, despite a small field of view, because the sensitivity region is localized. This demonstrates how tip coils eliminate one of the key limitations of external coil-based imaging. Here, let's see the second part. Let's take a look at the current MRI catheter visualization techniques. As shown here, these methods can be divided into imaging techniques and tracking techniques. Passive catheter tracking is real-time imaging, but not actively tracked. This is technically an easy method. However, the catheter goes out of the imaging plane, you lose the catheter position, which can be dangerous. Active catheter imaging is also real-time imaging, but still relies on less location, and it doesn't provide active tracking. Active catheter tracking provides active tracking but doesn't offer real-time imaging. It overlays catheter position onto pre-acquired 3D anatomy. Lastly, catheter tip imaging is both real-time imaging and active tracking. It's the key strength we are interested in today. It's important to note that the first three are the imaging techniques, while the last one, active catheter tracking, is a tracking method. But how do these imaging methods actually look on MR scans? Let's compare them slide by slide. These are most widely used imaging methods today. including passive catheter tracking and active catheter tracking. In passive catheter tracking, susceptibility artifacts caused by metallic or paramagnetic materials leads to signal void, which appears as a black dot, but it's only visible when the catheter tip is exactly in the image slice. Active catheter imaging uses microcoils to actively receive local MR signal, resulting in bright signal around the catheter tip. This improves visibility, but still depends on the slice position, so the catheter must always in the image plane to be visualized. So while both passive catheter tracking and active catheter imaging are slice-based, this means that whenever the catheter tip moves out of the imaging plane, it simply becomes invisible. To keep it visible, we have to manually adjust the slice position, which is highly operator dependent. This makes it difficult to use in automated navigation or 3D tracking systems, particularly in large space like the heart cavities. In addition, the passive catheter tracking, the susceptibility artifacts may obscure important cardiac structures. This schematic illustrates how conventional catheter imaging works using slice-based techniques. The catheter tip is only visible when it's within the image slice. That means if we miss the tip, it may not be seen at all. Let's see how catheter tip imaging works. One of the biggest challenges in catheter-based MRI is that the tip often disappears from the image. This happens because the wire runs parallel to the mean magnetic field, and as we approach the tip, the current drops to zero. With no current, the B field becomes too weak, so the scanner cannot generate a signal, and we see what looks like a black hole at the tip. To fix this, we add a small tip coil made from insulated wire wound in reverse, forming a solenoid structure. This coil redirects the current toward the tip and creates a strong local transverse B field, making the tip clearly visible in MRI. You can see the difference in the finger. On the left, without a coil, the signal drops out. On the right, with a tip coil, the signal is stronger and continuous. About 30 years ago, João Lima and his team came up with a really forward-thinking idea. What if we could actually bring MR inside the vessel by using a tiny catheter coil? It was a bold concept at that time, showing that intravascular MRI could be visualized the vessel wall and even plaque structures with almost microscopic detail. As shown in the left image, this clever design from Lima's group was very the first attempt to integrate an MR coil into a catheter. On the right is the actual phenotype they built in 1996. It allowed them to place a receiver directly inside the vessel, which was revolutionary at that time. But the imaging performance was still limited by the technology back then. Now, with much better hardware, faster imaging, and MR-compatible catheter systems, we are taking the same original idea and pushing it further, focusing on the catheter tip imaging and exploring how coil-oriented and forward-looking solenoid design can make interventional MRI more precise and reliable. Inspired by Lima's original concept, our design takes one step further. On the left, we show a schematic illustration of the coil structure. We use a finger of 8 1D pattern to construct the solenoid coil at the catheter tip. This configuration can help generate a magnetic field perpendicular to the catheter axis, which enhances the local MR signal at the tip. On the right, you can see the original MR images we acquired. This is a clearly visible bright ring around the catheter tip and no dark centerward, indicating that the coil is manufacturing well and the coil is functioning well and providing focused signal coverage at the tip. This illustration nicely summarizes the transition from conventional slice-based catheter tracking to tip-based localization. In this example, we inserted a catheter into a banana just to mimic real tissue in the MR scanner. Catheter tip localization using a localizer on the top row. We can clearly identify the catheter tip in axial, sagittal, and coronal planes. Then, by turning off the surface coil and activating only the tip coils, we acquire the image below. As you can see, the signal quality is excellent. We can clearly see the internal structures of the banana and its sharp outer boundary. Here we show some preliminary imaging results from our research team. This is how we designed and built our intravascular tip coil system. On the top left photo, you can see the real phenotype. Two sets of copper rods are wound in orthogonal directions at the tip, forming a dual coil structure. On the right side, we illustrate two different connection configurations. Figure 1 shows the two-channel setup. Each coil is independently connected to a separate MR receiver channel, C1 and C2, going through the Imicore and Siemens coil interface, and then reaching the Siemens 1.5 Tesla interventional MR system. Figure 2 shows the one-channel configuration. Both coils are merged and connected to a single channel. Here are the imaging characteristics of the catheter tip coil in different positions. At the catheter tip itself, as shown in the bottom left image, we observe a strong signal but also a noticeable artifact due to the very high local sensitivity. However, just a few milliliters away from the tip, as in the top left image, we still get good signal intensity, and importantly, the internal structures of the banana remains clearly visible without artifact. This suggests that even though the tip may produce artifacts, the nearby regions are still suitable for diagnostic imaging. Moreover, we can also acquire images from lateral direction, as shown on the right. Finally, this setup also allows us to perform functional imaging, such as T1 mapping, as shown in the bottom right figure here. Here we show preliminary results comparing surface coil and catheter tip coils for high-resolution imaging. On the top row, both imaging were acquired with T2 TSE sequence at identical resolution. While surface coil already shows the structure clearly, the catheter tip coil provides even stronger signal intensity and sharper edge near the tip. For the lower row, we use clinical LGE imaging parameters identical to those used in real patient scans. This surface coil image shows a little blurred boundary, and we also notice background artifacts, In contrast, even with a smaller voxel, the catheter tip coil imaging presents much more detail and better localization. Here we required the images with 3D printed heart phantom. We run localizer in coronal, sagittal, and axial planes to determine the catheter's position in 3 dimensions. Then imaging was performed at the catheter tip, as shown by the red arrows. Even with tiny 1 mm gap between different parts of the printed model can be clearly seen here. Here we compare surface coil imaging and catheter tip coils imaging at the same anatomical position with similar imaging parameters. The image in the middle is acquired with a surface coil, and the one on the right with the catheter tip coil. As we can see, the catheter tip image shows sharper structures and much more signal inside. These findings suggest that catheter tip imaging provides higher SNR and improves anatomical clarity in localized area. But how can we quantitatively confirm these imaging advantages? Here we can see the comparison with of signal to noise ratio between the catheter tip coil and between the catheter tip coil and the conventional surface coil. On the left side, you can see our phenotype catheter tip coil. It was mounted with a phantom and scanned in an MRI system. In the middle, we have the SNR map obtained using the surface coil. The image was acquired at the level of the catheter tip. As you can see, the center SNR remains under 40. On the right side, we see the SNR map obtained using only catheter tip. With imaging also performed at the catheter tip level. Here, the SNR is significantly higher and highly localized. The high SNR area is much broader. It's around 70. This highlights the strong advantage of catheter tip coil in achieving high local sensitivity. In conclusion, our work demonstrates the feasibility and potential of catheter tip-based imaging for localized high-resolution detection. We believe this approach can open up a new possibility in MR guided cardiac interventions. Thanks for your attention. I'd also like to thank to Sudabe, Imikor, all my colleagues and Yukshviter for their great support and through this work.
Very good. I have to activate. Yeah, thank you very much, Meng. This was a great talk. I think you should go. You should mute your laptop because it's sitting next to me. So thank you very much, Meng. It was a clear and well done presentation, and I think we see that there is some potential in this technique that we can go for very high resolution imaging if we have the possibility to go with the coils into the heart. Other questions?
No.
Maybe I have to say that we did the imaging with the conventional surface coils to put them very close to the object, that we have like a reference image. In humans, we would not be able to put the surface coils so close to the object, so we would not get these good images, but we wanted to put the surface coil like on on the surface of our object to have the reference image, and then to see how close we can get with the catheter tip coils. And you saw in this late enhancement image where we put the parameters that we use in humans, then the late enhancement is quite blurry compared to what we could get with the catheter tips. We should not underestimate the high spatial resolution that we still get in humans for late enhancement. These are structures that are about 15 millimeters in size, this little star. It's about 15 millimeters large. So it's the thickness of the myocardial wall, or a little bit more than that. So it looks a little bit blurry if you go for the parameters that we use in humans, but we are now already more or less at the point that we could see conducting channels with these techniques. And I think with tip imaging, we can go much further. I think it would also be very useful to check where we want to burn. So before we would ablate, we can acquire these very high resolution images to make sure that we are at the right point, that we see the channel. Then we can burn, and we can check with these coils what is the lesion that we created. And I think also, for example, before taking biopsies or so, it would be very nice to localize exactly with such coils where you are before you use the biotome. I think are there questions anyone needs to, I think there are no questions in the chat here, and so if it is okay for you, I think we go to the next speaker, right? It will be Marco